Hello, this is group 3 and our research topic is measurements of frequency, wavelength and voltage standing wave ratio. I'm called Atware Sandra and my group members are Arnett Prosper, Nabasa Agatha and Muchunguzi Felix. I'm going to take you through frequency measurement. Frequency is the number of occurrences of a repeating event per unit of time, and it's measured in hertz, where 1 hertz is equivalent to 1 event per second. Frequency is an important parameter used in radio frequency engineering to specify the rate of oscillatory and vibratory phenomena such as mechanical vibration, audio signals, radio waves, and light. And I'm going to take you through the ways of measuring frequency, that is digital counter timers, phase locked loop, and a stroboscope. Let me take you through the digital counter timers first. This is the most accurate and flexible instrument for frequency measurement. It has an inaccuracy as low as 1 part in 10 to the power 8, and it measures all frequencies between DC and several gigahertz. This is how it looks like. It contains an oscillator, a shaper, divider, an electronic gate, a counter, a memory for storage, and the display. The oscillator is usually placed in a regulated temperature environment so as to provide a reference frequency that is very accurate and stable. And that reference frequency generated is fed into the shaper, a pulse shaper, where it is transformed into a train of pulses that are fed into the gate. Then the signal whose frequency is going to be measured is also fed into the shaper and transformed into a train of pulses that are fed to the electronic gate. So the train of pulses from the oscillator that are fed into the gate open and close the gate, and the pulses from the input signal enter the gate for the time which is opened by the pulses from the oscillator. And this counter here counts those pulses that get through the gate for the time it's opened, and they are stored in the memory and displayed. That is the frequency. Those pulses that enter the gate are proportional to the frequency of the unknown signal, like the frequency we are measuring. And this is what I've been explaining. Now let me take you through the phase locked loop. A phase locked loop is a circuit consisting of a phase sensitive detector, 2 amplifiers, and a VCO, voltage controlled oscilloscope. The signal whose frequency is going to be measured is amplified, that is, it's fed into the amplifier, it's amplified and fed into the phase sensitive detector. Then also another signal, which is an output from the VCO, is also fed into the phase sensitive detector. This phase sensitive detector compares these two phases, that is for the input signal and for the output of the VCO. If there is a phase difference, that error signal, that phase difference is an error signal, and it's amplified and fed into the VCO. When that signal is fed into the VCO compares that error signal, sets the VCO to a certain frequency. That is, the VCO is locked to a frequency, and that becomes the frequency of the signal, like the frequency of the unknown signal, the one we are measuring. So we are able to obtain the frequency of the signal. Yes, like you see here, they're saying the DC output from the VCO is then proportional to the input signal frequency, as in the frequency of the signal we are measuring. Now let me take you through the stroboscope, which is our last instrument, and this is used for measuring the frequency of rotating or vibrating objects. It works in a way that this strobe light is the flashing light from the stroboscope, and this light is pointed to the rotating object or the vibrating object whose frequency you're going to measure, and the probe is adjusted up and down, like the frequency is adjusted up and down using the probe. When the frequency of the probe equals the frequency of the rotating object, the object completes one cycle of oscillation and returns to its original position between the flashes of light. So when illuminated by the strobe, the object appears stationary. The frequency can then be read from the calibrated readout of the stroboscope. That is, if the stationary, like the rotating object appears stationary, the frequency is then read out. But this instrument also has a drawback, that is, an object rotating at an integral multiple of the strobing frequency will also appear stationary. This is its drawback, because you won't be able to get the right reading. Thank you. Let my colleague Felix take you through wavelength measurement.
Okay. Similarly, we shall have the same procedure with wavelength. We shall know what wavelength is, how to measure it, the various instruments we need, and then get to know the drawbacks of each instrument. So with wavelength, definition is it's the distance covered by one complete cycle of the electromagnetic wave. Similarly, it's also the distance between two peaks of a wave. We've happened to draw sine waves all through, and gotten to know that with wavelength you get two peaks and then take the separation, which is the distance, and this is measured in meters. So now we get to know how we can measure wavelength. In simple terms, measuring wavelength, we start first of all, we get a measuring instrument that will measure the energy, and we're using a photometer in this case to measure the energy of the wave. So after measuring the energy of the wave, we convert the energy into joules, the units for energy. Then divide the energy by Planck's constant. The symbol for Planck's constant is usually h. So we divide that energy by that constant to get the frequency of the wave. That is, energy is equal to h f hc. So then finally we divide the speed of light by the frequency to get the wavelength. So we also have the alternative to calculating that by using the wave number. If we give another wave number, we note its units and then get 1 and divide by the wave number to get the wavelength. That means wavelength will equal to 1 divided by wave number. So now we get to the different instruments we can use to measure wavelength. We have two. We have the laser wavelength meter, and that is the drawing. You can clearly see that. So this instrument is a precise instrument with an accuracy of 0.2 parts per million, and prior to using this instrument we always advise to calibrate so to achieve high accuracy. The other instrument is the optical wavelength meter. It's also easier to use because it requires a minimal setup, and then the key factor it has a panel display that makes it easier to read off the measurements. That means it's straightforward to get the readings from this meter. So the other things we need to note are the aspects you need to know before selecting a wave meter. You need to look at the accuracy of the meter, depending on the accuracy you need, because with some meters it varies. Find some need bigger accuracies. Say for the previous one we had, it has an accuracy of 0.2 parts per million. So if your accuracy requirement is within that, you would go for the laser wavelength. And the other thing is you need to know the reference, internal reference. You also need to know the measurement speed. It always varies with the meters. Then finally, we also need to know the the various types of errors that affect our measurement accuracy. We have length drift, and that is usually caused by drift in temperature. Second, we have imperfections or changes of the beam profile, and then finally we can have fluctuations of the input power, and then detector noise. Thank you.
This is Prosper taking you to the next one, which is VSWR, which is the voltage standing wave ratio. As you can see, the subtopic is all about the ratio, so therefore we expect fractions. And the definition of the voltage standing wave ratio is how efficiently radio frequency power is transmitted from a power source up to the antenna through a transmission line into a load, for example the power amplifier, and then to the antenna. So an ideal system has 100% efficiency, and the energy is transmitted as it is outsourced. The way it enters is the way it gets to the other side. So this requires the exact match between the source impedance, characteristic impedance of the transmission line, and all its connectors. Here impedance, which is the total effective ohmic resistance and reactive resistance. So we have that for an ideal system, 100% of the energy is transmitted. The signal's AC voltage will be the same from end to end since it runs through without interference. Then for real systems, there is a mismatch of impedances. So the power, some of the power is reflected back from the source. So those reflections, they cause destructive interference and leading to peaks and valleys in the voltage at various times and distances along the line. This is what VSWR is all about. So voltage standing wave ratio measures these voltage variances. So it's the ratio of the highest voltage ending along the transmission line to the lowest voltage. Since the voltage doesn't vary in an ideal system, its ratio is 1, because the high will be the same as the low, since it's consistent. And it's expressed as 1, as this 1.0, or as a ratio 1:1. Then when reflections occur, the voltages vary and the voltage standing wave ratio is higher. Let's say 1.2, or this way it's represented as 1.2:1 or 1.2. So we have said it's a ratio, and it's given to us as this mathematically: Vmax over Vmin, where Vmax is the maximum voltage of the signal along the line, and Vmin is the minimum voltage of the signal along the line. And this can be derived from impedances. Let's say voltage standing wave ratio is equal to 1 plus and 1 minus, which means the 1 plus is standing for the maximum, and this goes for the lowest. Then they are explaining the above equation from the impedances, where gamma is the voltage reflection or efficient near the load derived from the load impedance and the source impedance. So we are having our from impedances, we are having load impedance minus source impedance over load impedance plus source impedance, which is giving us the same value for the VSWR. So if the load and transmission line are matched, let's say their impedances are matched, the voltage standing wave ratio will be 1. So it will be back like to the ideal if they are matched. So it will be 1 or 1.1. Yeah, thank you.
This is Agatha, and I'm going to take you through how you measure VSWR using the VSWR meter. And we have two cases when the VSW is low and when it is high. For when it is low, that is below or less than 20, these are the steps that you go through in measuring its value. This is the block diagram that is used, and this is how it flows. You have the microwave source where a signal is put. Then you have the isolator, you have the frequency meter, variable attenuator, slotted line carriage, you have the detector, you have the device under test, you have the load, and you have the VSWR meter. So you energize your microwave source with a 1 kilohertz square wave signal as a carrier. Then you adjust your tunable passive components until you get your VSW meter to read 30 decibel, and then your detector is adjusted to get the maximum power across the VSWR meter. You move the slotted line carriage towards the source to find the standing wave minimum position, and then you adjust your control knob of the VSWR meter and the attenuator reading across the VSWR meter until it reads 1 or 0 decibels, and this is called normalization. So you normalize the VSWR meter. So, and again you move your slotted line carriage towards the source to find the next minimum position, and then the reading on the meter is the ratio of the magnitude of reflected signals, minimum and maximum voltages. Using this formula, you are able to calculate your VSWR value, which, as given previously in the mathematical expression as Vmax out of Vmin. And then our VSW meter has 3 scales. One is from 1 to 4. The second one is from ranges 3.2 to 10, and the third scale is from 1 to 1.33. So you use these ranges or these scales accordingly in reference with your device under test. If your device under test is having a scale of 1 to 4, you use scale 1. If it is having a scale of 3.2 to 10, use scale 2, and then if it has a scale of 1 to 1.33, you use scale 3. And if the device under test is having a range of VSWR of 10 to 40, a 20 decibel range is selected in the VSWR meter, and reading is taken from the first scale from the top, which is then multiplied by 10 for getting the actual reading. And remember, the first scale was from 1 to 4. For high VSWR measurements, that is above 20, we use the same procedure, but we do not use the same procedure because the detector may not be tuned to work in the square law region. So we use the double minimum method. Here we use the same block diagram as this, and this is how you adjust to get your value. You energize your microwave source with a 1 kilohertz square wave signal as the carrier. You adjust your tunable passive components to adjust the reading of the VSW meter to 30 decibel scale, and then you adjust your detector to get a maximum power across the VSWR meter. Then move the slotted line carriage towards the source to find the standing wave minimum position, and we let that position to be D1. Also, again, you move your slotted line carriage to find the next immediate minimum position, and you let that position be D2. From those, you can determine your wavelength using the formula shown, 2 into D1 minus D2. And then by adjusting your control knob of the VSWR meter and the attenuator, the reading across the VSWR meter is adjusted as 3 decibels at this minimum position. By taking this point as reference, slotted line carriage is moved on either side. Then the points which the VSWR shows 0 are noted and are marked X1 and X2, and you can use this formula to obtain your VSWR meter R value, which is S. Since you already have your wavelength and your knob pi as a constant, you can substitute the values of X1 and X2 obtained to get your VSWR value. Thank you.